one? All right, fine. If there's anything we've seen from the last few talks is that in any catalytic process, in any microporous catalytic process in particular, there is a lot going on. All right, so you begin with things like the uptake of your fluid into the particle or your gas into the catalyst particle. You've got your microscale dynamics, be that the mass transport of your mixture through the catalyst particle, all the way through to your nanoscale dynamics, that's your molecule swimming around in the zeolite cages and the zeolite pores, all the way through to when you get to the molecular scale. So when your molecule of interest gets to the active site, and ideally what you want to happen takes place. All right, and the molecule that you want to get out is what swims through the cage on its way out, the structure on its way out, and then out of your particle again. We're really fortunate. We have so many different techniques, incredibly powerful techniques and complementary experimental modeling techniques, which can take through all of these scales. So on the molecular scale, we had spoken about already density functional theory calculations, which are paired really well. Again, we've heard already, vibrational spectroscopy experiments. Okay, I'm going to talk to you about some of those in a second. On the nanoscale, something you guys may know a little bit less about, and I'm going to take you through a bit of that. This is a technique of quasi-elastic neutron scattering. And that pairs brilliantly with classical molecular dynamics. So more simple, but larger, and actually just as powerful modeling techniques too. And then on the slightly larger scale, I haven't been able to work on these yet. These are things like pulsal gradient, NMR, gravimetric absorption. And you need to understand really this entire thing before any of this actually becomes too relevant. So throughout my career, I've been able to work on these two scales here. Okay, so the nanoscale and the molecular scale. As Chris said about being one of their own, I was fortunate enough to be able to do my PhD at one of the most world-class facilities there are. So I was basically UK Talbot did most of my work at the ICIS neutron source. And I employed neutron spectroscopy to study a lot of catalytic systems relevant to a lot of the talks we've heard today. I won't take too long, but I think sometimes we forget how incredible some of the technology behind the techniques we use actually are. Now, for those of you who don't know, you start off with hydrogen gas. That is split into hydrogen ions. That creates a proton beam, which then is sped up to 80% the speed of light. That is zoomed down to a tungsten target. The protons hit the tungsten target, and that sweats neutrons. Okay? Those neutrons are then guided to the instruments via these kind of super reflected mirrors. They're scattered up our zeolite sample. They hit a detector full of helium-3. Helium-3 becomes unstable, undergoes a fission reaction. Those two fission products, based on how quickly they hit the anode and cathode on the detector, you can work out the time of flight of the neutron versus energy change. That's neutron spectroscopy. And based on how quickly the positive and the negative ones hit each side, they know where it hits in the detector. And you can use something called Q, momentum transfer. Okay? This is stuff that we take for granted when we use neutron spectroscopy on a regular basis, but I think it's important to understand what goes into it. Now, we had a brief introduction from Sihai, actually, about the kind of power of neutron spectroscopy. Crucially, it's uniquely sensitive to H1 hydrogen. That's very, very useful if you have a hydrogenous molecule swimming around inside an inorganic material, an organic cage. The neutron goes through, just interacts with the hydrogenous molecule inside. Highly penetrating, great if you're trying to look at what's going on in the bulk of the structure. Okay, but crucially, that kind of means you often need larger samples because they don't interact too strongly. That's changing. We need smaller and smaller samples all the time, year on year now. No selection rules, okay? So A, you can model it very easily with classical dynamics, as I'll show you in a minute, and you've got the entire spectral range available. So you've got this quasi-elastic region, which is tiny energy transfers, kind of 8 wave numbers or so, or milli microelectron volts. So you can look at translational motion, you can look at rotational behaviors, you can go all the way through to vibrational spectroscopy, all of which is in what I'm going to talk to you. Now, my favorite quote from Stuart here is that neutrons are democratic. So you can also say they're proportionally representative. They see what's there only in the amount that it actually is there. Okay, so these selection rules help massively. Now, I love nothing more than speaking to a whole room about the fundamentals of quasi-elastic neutron scattering. I'm not going to do that, but I'm conscious that you'll need something in order to kind of what I'm saying kind of makes sense to all of you. So basically, you have zero energy transfer, okay, and we're looking at tiny broadenings of this elastic line where there is zero energy transfer. Okay, so we're talking tiny energy transfers, micro electron volts to milli electron volts, just for some perspective. 1 milli electron volt is 8 wave numbers. These are the small energy transfers here, and they're related to translational motion of molecules and also rotational motions. How this energy transfer changes as a function of Q, that's the momentum transfer. That tells you about how the molecule can be moving. If it increases linearly with Q squared, you've got a Fickian kind of unhindered diffusive, almost liquid type diffusion that's taking place. Now, if you see a deviation from linearity, you see kind of an R shape, right? That's more like jump diffusion. That's very common in microporous materials, where a molecule sits at a place for a while, and then will jump a given distance, sit at another place for a while, jump a given distance. That's very common, and that's the kind of thing we see often in these sort of studies too. Now, again, that's all about how much this line broadens, and you can quantify how much that broadens by fitting a Lorentzian curve to that. One other thing that matters greatly, sometimes the molecule isn't diffusing. Sometimes it's sat there and it's rotating. It's undergoing a localized motion. This is where you use something called the elastic incoherent structure factor. What that means is how much of this elastic line is in terms of a ratio of how much of the total spectrum. Okay? And now you can fit this to a range of models. Now you could have, say, look at a methanol molecule here, that will come up. You could have one that is isotropically rotating. It's just rotating, no kind of real orientation to it, rotating in all different directions. You could have a methanol molecule that's anchored to one side, and its methyl groups are rotating. Or you could have something that's trapped in a cage and it's just rattling around inside of it. There are models that fit this elastic incoherent structure factor for all of these different things. And this kind of fundamental part, it's kind of underpinned all my research really, is that this experiment works on the same timescale as your classical molecular dynamic simulation. Now, we hear a lot about quantum mechanical simulations, particularly in catalysis when we're talking about breaking and making of bonds. But if you want to model thousands of atoms and you want to model diffusion processes, you have to use classical molecular dynamics. So it's a much kind of lower level of theory, but it's often parameterized after painstaking work to accurately represent the framework, accurately represent the molecule and the interactions between them. Even in the last 10 years since I started, there's been real leaps and bounds in this. People used to, they model the framework as a rigid body, and anyone who studies zeolites knows that actually we sometimes think it's a rigid structure. It's not. It's actually really dynamic. It breathes a lot. And when a molecule goes inside a pore, that changes the structure of the pore around it, and that changes how the molecule behaves. So if you make that approximation, you're missing out on a lot of potential behavior. You don't have to do that anymore. We used to have things like simulation sizes and simulation lengths. We can create these huge systems and get these very accurate statistics now. And also see behaviors that we wouldn't have seen before in the past, clustering behaviors, channel switching behaviors, that when the framework's breathing, it can access parts of the crystal that it wouldn't do otherwise. And all these make a huge difference to our observations and how we can help interpret our neutron data. Now, so at this point, I get to take you to a review for anyone's interested in this. This was a fundamental kind of seminal review here. And this is by someone named Hervé Jobbik. And anyone who's ever used QUENS or even really studied diffusion in zeolites will have heard this name. I could go about saying things like none of this, wouldn't have been possible to perform these studies without his contributions. No, this wouldn't be here to be done if it weren't for the innovations of this man in the 90s. So everyone who's worked on this wishes Hervé a very enjoyable retirement wherever he is and what he's doing, and thank him for a lot of his innovations in this field. Now, so my first case study is work that involves effectively studying alkanes, alkenes, hydrocarbons, and zeolites for the purposes of fluid catalytic cracking. This is a review by Beckhausen and Vogt. Some numbers in here that I find very interesting. It's estimated that 2,300 metric tons of FCC catalysts are produced every day. So that was in the US. And there's a lot of different parts to it. So you've got binders, you've got clays, that's help with heat capacity, but the active part is a zeolite catalyst, okay? And that's typically zeolite white. If you're trying to encourage production of ethene and propene, they actually put in ZSM5, okay? So ZSM5 is it's of great interest for a lot of studies in this kind of material, and this is actually where we first began. And we were trying to take these new, more accurate models that have been painstakingly kind of parameterized over the years, but not necessarily been allowed to be used to their full potential. And we looked at the behavior of long alkanes in these zeolites. We compared them to studies, previous QUENS studies from about 10, 15, 20 years before by Hervé Jobbik, measuring diffusion coefficients throughout these crystals. And what we found, when you allow the framework to breathe, when you have properly parameterized interactions between the hydrocarbon and the zeolite, from density functional theory calculations, absorption, energy calculations, you can actually measure a diffusion coefficient and an activation energy that comes from those diffusion coefficients to within experimental error. Okay, within experimental error of a QUENS experiment. Now, let me be very clear. These are mostly parameterized on a thing called a Lennard-Jones potential. That's two numbers. Okay, an epsilon and a sigma, two numbers. And you can run this calculation on a laptop. Take like a day, right? on an old laptop. And you can get to with an experimental error, and don't underestimate how powerful that is, all right? So another study, so this was actually with Professor Joubik. Actually, after he came to a Catalysis Hub event, we started this collaboration. And this was about the behavior of isobutane. It's a big, quite bulky branch molecule in ZSM5, in this case, the MFI structure. And use diffusion within these pores. It's quite hard to measure diffusion of these quite bulky molecules sort of on the nanoscale. This was done using neutron spin echo technique. Now, what they found was that they got a jump diffusion mechanism of isobutane through this structure. And that makes sense. ZSM5 or MFI has straight channels, and they intersect with these kind of zigzag channels. And you've got these intersections in the middle. It's typically assumed, right? You've got a 10 angstrom jump distance, which is what they observed. So they got this R-shaped kind of jump diffusion kind of mechanism that it would live at the intersections. It would then jump 10 angstroms to the next intersection. There's a slight issue here, which is that when you use something called the intermediate scattering function, that tells you something about the dimensionality of diffusion. They were finding three-dimensional diffusion, three-dimensional translation is taking place in the system. And that wouldn't be the case if it was just jumping from one intersection to another. It suggests somehow that the sinusoidal channels are playing a role. And they couldn't really quite work it out what it was, because every simulation done up until we started doing things was showing that the isobutane just lives in the intersection and jumps in a straight line down to the next one. This is when we talk about framework breathing, okay, modeling framework breathing, because actually the intersection isn't the happiest place for this molecule to be. What it is a small section of the sinusoidal channel. And that's what we were able to find, that actually it spends its residence time, as is found by the neutron experiment. It spends its residence time in this little section of sinusoidal channel, just bounces here up and down, and then makes that long jump after a given period of time, okay? So this is what we talk about when you have these relatively simple models, allow things like framework breathing. You see completely different behavior of the molecule, and that allowed us to actually explain what they were seeing in the Heinz experiment. Moving on to the next case study, we've heard a bit about methanol to olefins already. This is mainly done in the Chabazite structure, but methanol to gasoline or some other methanol to hydrocarbons processes, they take place in ZSM5. And I'm going to take you through this study because despite this being a catalysis award, I've only ever performed one reaction throughout my whole time studying, and it was a complete accident. And that was this. So the first aim was to take methanol, put it in HZSM5 and measure its diffusion coefficient. Simple enough. I wanted to compare it to zeolite Y. Larger pores, about 13 angstroms pores compared to the 5.5 angstrom cage structure, joined by windows compared to straight and sinusoidal channels. We dosed methanol into the system, and what we found was that actually there seemed to be no movement at all, which was a little bit concerning. We thought, well, we were here to measure diffusion coefficients, and we're not getting any. In zeolite Y, we found there was some quite healthy quasi-elastic broadening, and we weren't too sure what was going on. Now, the pore differences, I suppose they are significant, but not enough that you see here. So this red in the middle, that's what's happening at 10 Kelvin, and the blue is what's happening at room temperature. So there's about as much movement, almost at absolute zero in the system, as there is at room temperature. And that didn't quite make sense to us. So it was at this point we were able to use MAPS, which is a vibrational spectrometer. It's designed for magnetism, but the catalysis scientists are sort of taking over at the moment to use for vibrational spectroscopy. And here's what we found. So actually, if you see methanol at the top, that's pure methanol. And do you remember what I said about low energy modes? So I can get the whole spectrum. Look at the clarity with which we're seeing the OH deformation mode here at kind of 600 wave numbers. Okay, so this is pure methanol, and then this is methanol dosed into the zeolite Y catalyst. What you can see is some broadening, some shifting, suggesting that there's quite a strong interaction of the OH group with the acidic sites in the catalyst, despite the fact that it's able to diffuse. Then we got a bit of an explanation as to why perhaps we weren't seeing the motion in ZSM5. So keep your eye on this OH deformation mode here, how it broadens in HY, because in ZSM5, it disappears completely. So what seems to have happened is we've dosed methanol in at room temperature, and we've lost its OH groups. Now, what we can do is if you change the instant energy of the incoming neutron, you can actually look in a bit more detail at the lower wave numbers. So again, we're able to resolve this OH peak here in methanol. We see it broadening in line with quite a strong interaction. And then in ZSM5, disappears completely. So what we appear to have is a static system without any OH groups. And now we heard a bit about trimethylioxoniums from Sihai's talk as well. And then they came into, later on, you find what's typically surface methoxy. So methanol interacts with the Bronsted site, water's kicked off, and then you create this surface-bound methoxy, and that's kind of a feedstock species for the next carbon-carbon bonds that come through. What's crazy is this is happening at room temperature, okay? And again, this is, just wanted to confirm that this was the case, and we did this using density functional theory, perturbation theory. You can create the vibrational modes, or model, sorry, the vibrational modes. You can then use a software called A-Climax, developed at ISIS, and you can account for neutron cross-section. You can basically reproduce your INS spectrum. And Arun Shuti and Matt Barrow did this, and we got quite a nice, nice matchup in terms of the modes that we saw. I suggest, yeah, we are producing the surface methoxy species. Now, it's fair to say there's been a fair bit of debate as to whether this is exactly what we're seeing. Some people would say, we're not sure. We think perhaps what's happened is it's massively broadened out the peak, right, to the point where it almost seems invisible, to which I would say, possibly. Some people would say, well, actually depends how much you load in. If you load in enough, that creates a really nicely hydrogen bonded cluster of methanol molecules, and that easily stabilizes for you to perform that surface methoxylation reaction, to which I would say, yeah, possibly. Other people would say, actually, it depends how you load it, right? If you're loading in under flow, the water that's produced, which would otherwise hydrolyze that surface methoxy, is brought out the system. So that encourages the formation of these surface methoxies and for them to be, to maintain, to which I would say, yeah, possibly. There's a lot of yeah, possibly about this. And so much work has been done to get to the bottom of this since then. And to some excellent work by people in the room, even Santosh, Andy, and Richard, of course, and yeah, plenty of people who have worked on this. And it's great to have been part of this project and this kind of mission to find out what's really going on, both computationally and experimentally. Moving away from pristine systems, this is some work I've got to do with Santosh, Russell Howe, and Dave Lemon, and others. And this is the effect of MTG catalysis on methanol mobility in ZSM5. And we took 3 samples. We took a fresh catalyst, ZSM5 catalyst, and we dosed methanol into it. We took a zeolite catalyst, which had had the methanol to gasoline reaction taking place in it for about 3 days at 623 Kelvin. The idea then was to create a hydrocarbon pool. So the understood mechanism by which hydrocarbons form, this hydrocarbon pool, building it up in the pores, coating them up after about 3 days so that you can block the pores and actually watch methanol slow down and to a complete stop. So that happened at 623K, 623 Kelvin, and one who had MTG catalysis performed at 673 for 30 days. So we're really trying to block up these pores and show that methanol stops diffusing. Now, we took our fresh catalyst and we took our ZSM5 623, as I'm going to call it, ZSM5 with MTG performed for 3 days at 623 Kelvin. And what we found was there wasn't any movement in either of them. Okay, so that was all a bit frustrating. But here's what was weird, because we took the sample that was meant to be most blocked up, right? And rather than showing very little movement, either because of hydrogen bonding or methoxylation, whatever you would like to say has happened, that was the one we saw movement in. The one that was meant to be most blocked up. Really surprising, okay? First thing I wanted to do, and while I can see here again, you've got this healthy quasi-elastic spectrum in the one that's supposed to be most coked up or blocked up. And I wanted to find out, first of all, what kind of movement is happening, okay? Because that's going to lead us to what might be going on. So there's a few models. I told you about the elastic incoherent structure factor. You can then use that to fit a model to it and work out if you know the radius of the molecule you're using, its radius of rotation, or the radius of the sphere that it's supposed to be rattling around in, you can create this EISF. What we found was that none of the pure models work, but what we did find was that if you take isotropic rotation, so a freely rotating methanol molecule, and you say 42% of those molecules are not moving, you get a very good fit for the data. Okay, so it makes sense. There would be a lot of these molecules that aren't moving, the rest are isotropically rotating. You can get a rotational diffusion coefficient from the width of that quantum spectrum. And we're able to get quite a sensible rotational diffusion coefficient. It's small in things like propane. We've reproduced this in different systems, different silicon to aluminium ratios. They all kind of match up. So we're confident that it is rotational. Well, it's this isotropic rotation. And but that doesn't tell us anything about why it would happen in the sample that's supposed to be most blocked up. Turns out you're not just blocking it up, you're destroying it at 673 Kelvin, right? And this was some excellent NMR and porosimetry work. This was by Santosh and I believe Russell, who used NMR to show that we're losing framework tetrahedral aluminium the more the higher temperatures that we carry out this reaction. Okay, so NMR was showing this, and the porosimetry was showing that we're creating mesopores by bringing out this aluminium from the framework. So you're not just blocking it up, you're removing aluminium from the framework, creating mesopores and giving the methanol more room to move around. So this was quite an interesting study showing the effect of catalysis both on the framework or the catalyst and the resulting behavior of the reactants. You can see some quite counterintuitive behaviors that actually, once you properly characterize your sample, actually become quite intuitive. This was a really fun collaboration next. So we've heard a bit about ammonia SCR as well. This is with Johnson Matthey. And we've got this on the front of PCCP, but the SCR process, just for those who just need refreshing, this is how you take NOx gases in the back of every diesel catalytic converter using copper chabazite, which was mentioned earlier. You can turn that NOx into harmless nitrogen and water. And Johnson Matthey, who are using chabazite catalyst, they wanted to know how their reductant, so in this case ammonia, how it behaves in their catalyst. Crucially, as a function of composition. Okay, so if you change silicon to aluminium ratios, or if you have these whopping great copper counterions, which typically live in the windows, but as soon as you dose something in, it's drawn into the cage. How does that affect the behavior of ammonia? So we formed a Quenz experiment, and it turns out that if you take a sample with no copper counterion in it whatsoever, and you take a sample with quite a lot of copper counterions in it, and you take a Quenz spectrometer, which measures movement over 100 picoseconds or so, you see no difference whatsoever. Now, that's interesting. So first of all, we find that we see this jump diffusion mechanism. So you've got a residence time kind of 15 to 25 picoseconds, and then a jump distance of about 3 angstroms. We'll get to the modeling later, but we consider that this would be jumping through the cages. But crucially, why would the copper ion not change anything? And this is where our modeling really helped us. Okay? What our modeling showed was that actually the ones that are jumping quite happily, because the ones that are interacting with the counterion are interacting with the counterion and they're shielding everything else. They're basically, any ammonia molecule that's moving around isn't being able to see that copper counterion. It's not able to see the copper counterion because you've got such strongly absorbed ammonia molecules just coating that site so that it can't be seen by the rest of them. So it shows the importance of loading, right? If you really want to use every active site as effectively as possible, you need to have the right loading, because some of them will just block off your species and not be able to react, okay? So this is our trajectory plots. They're showing that we're getting this diffusion through the 8 rings, and those that are absorbed are absorbed, and those that aren't don't even notice it's even there, okay? Now, JM were also interested in chabazite's 2-dimensional sibling, which we'll call levinite, so LEV zeolites. Now, they're very similar building units, you can see, very similar cages. So the chabazite cage and the levinite cage are quite similar, but the levinite cages are arranged in a way that diffusion is only permitted in 2 dimensions, okay, as opposed to 3 dimensions, which is the case in chabazite. So we're interested in saying, okay, so what is the overall difference in diffusivity? And you never guess what? When you take a Quenz spectrometer that measures time over about 1 to 100 picoseconds, you see very little difference again whatsoever. You do see a difference qualitatively in terms of the confinement. I'll come to that at another point, but you see the same jump diffusion mechanism which takes place throughout the structure, throughout these 8-ring windows. What happens when you run your MD simulation? Do we see any kind of further things in this? Well, one thing you can do, I'll come to this a little bit later on, is that just for a couple of Fourier transforms, you can basically create your modeled Quenz spectra from these classical simulations. We found the same jump diffusion mechanism taking place when we used our classical simulation too, again, showing in our ND simulation that this jumping through the cages is taking place at the same rate. Slightly different when you analyze the ND simulation on the nanoscale though, because we run these things for a few nanoseconds and we'll just chop it into chunks and just and see what's going on at each chunk. But if you run the whole thing, it was telling us, actually in chabazite, the diffusion coefficient is about twice that of the one in levinite. So the question, I suppose, is it the difference in dimensionality? Is the fact that one can only allow diffusion in 2 dimensions, whereas the other one allows it in 3? The answer is actually no, because while you have 0 diffusion in the 001 direction, as you'd expect with levinite, you look at the y-axis here, what you're finding is that the diffusion, even in the dimensions that are allowed, are only half that of the ones in chabazite. So why would that be? And what you do is you've got to drill all the way down to the building unit itself. Because remember how I said it jumps through the 8-ring windows? And the Quenz was showing that it jumps through the 8-ring windows at the same rate. What it doesn't tell you is how many of those windows there are. And in chabazite, the building unit, despite being a really similar size, has double the number of windows. And so really the same rate of jump diffusion is taking place, but there's double the number of geometric opportunities for that molecule to perform that jump. And that's what leads to, on the nanoscale, a doubling of the bulk diffusion coefficient, despite that on the kind of picosecond scale, if you want to call it that, the same movement is taking place. So that's quite a clear illustration of this kind of structure molecular behavior relationship. So yeah, just a final slide to show the importance of kind of looking through from picoscale through to nanoscale and where you can get these differences. So just my final case study. And this is on biomass utilization with zeolite catalysts. Now, this is an excellent review by NARTS in ChemSoc Rev, showing the potential of zeolite catalysts, Bronsted acid zeolites, noble metal zeolites, Lewis acid zeolites, and what they can do for biomass conversions. Now, for these studies, what we're most interested in here is this section here. So taking lignin, turning it into methoxy or alkyl phenols, and then later on the kind of aromatics and alkenes. And we wanted to understand how these kind of more simple species, kind of these model molecules, how they behave inside zeolite beta. Now, zeolite beta has been mentioned already, and so it's kind of it's between ZSM5 and zeolite Y in terms of pore size, about 6.5 angstrom channels, okay, going through it. And we took phenol, and we took its larger sibling, catechol. So 2 OH groups in one, just the one on the other. And we just wanted to know, how does the difference in diffusivity, how is there a difference in diffusivity in zeolite beta? What happens when you change the ratio of zeolite beta, among other things? And so we formed our Quenz experiment to look at the behavior of phenol and the behavior of catechol. And what we were able to do, we were able to take our models of motion, in this case, be isotropic rotation with the radius of a phenol or catechol molecule, whether it's rattling around in a cage or whether it's anchored to a site and it's just the ring that's rotating. And here's one thing that's quite interesting. We found that despite catechol having that extra kind of whopping great OH group on it, in these quite constricted pores, they actually rotate at very, very similar rates. But one thing that's different is in our experiment, 40% of the phenol molecules were immobile, 61% of the catechol molecules were immobile. So that suggests that this extra OH group here, either due to sterics or possibly due to this extra kind of ability to hydrogen bond with a Bronsted acid site, is hindering it significantly to the point where about actually relatively 50% of the molecules are immobile, 50% more, sorry, of the molecules are mobile. But the ones that are allowed to move around at the same rate. Now, we can conventionally as well use our molecular dynamic simulation to go about measuring bulk translational diffusion, as I showed you before. We're able to show a few things. First of all, that in terms of the bulk translational diffusion, you get significant differences when you, say, have a silicon to aluminium ratio of 12, which is what we would use for our commercial catalyst, compared to a fully silicious beta sample, which we can synthesize. So difference in diffusivity by about kind of factor of 5 to 10. Okay, that extra OH group on the phenol, in terms of the full-on diffusivity, that hinders it by a factor of about 4 to 7. Okay, so that's quite significant as well. And the great thing about Quenz and MD is, I've sort of already spoken to, is that you're only kind of a Fourier transform or two once you've got your atomic displacements away from actually reproducing a Quenz spectrum. Now, I won't go too far into this, but what I'll say is that through this rather simple sine function here, you can create what's called the intermediate scattering function, which is basically a Fourier transform of your dynamical structure factor or your Quenz spectrum, effectively. So once you've created these, there's two things you can get. There's the baseline, where this intermediate scattering function converges. That is your kind of configuration after infinite time. That's geometry of motion. That's your EISF. The decay constant, so the decay constant of this intermediate scattering function, that's your broadening of the Lorentzian. Okay, so that's basically your rotational diffusion coefficient in that sense. You can create both your widths and your EISF from just the humble, simple classical molecular dynamics simulation. So we were able to do that. So we created an elastic incoherent structure factor, sorry, modeled, I'm going to say we created it. We modeled a elastic incoherent structure factor, and we found that when you input the correct radius of a phenol molecule, we're actually able to fit our modeled EISF to the model of isotropic rotation, which is what we fit our experimental data to. And we were actually able to show that both with these phenol, both with catechol, rather than phenol, but also using our acidically modeled zeolite compared to the pure silica zeolite, that you need to fit using this larger immobile fraction, like I spoke about when we were modeling the data. Okay, so we're able to show both kind of on the kind of nanoscale and the picoscale, and actually reproduce our Quenz data from this relatively simple simulation. We're able to take the rates of rotation, again, from our molecular dynamics simulation, and we're able to get well within experimental error of a Quen's experiment too. So we're able to use the humble MD simulation just to model diffusivity, to model rotation, and again, with a properly parameterized set of simulations from people who have been doing this for decades before us, even before these long simulations could even be performed. We're able to model and actually really reproduce our spectra, and then start predicting these kind of outcomes too. So just some future work. Now, this is something that's going on. My PhD student Katie, who's based at the hub, she's looking at cresols. We're moving on to things like stringols, geocols as well. But the important thing, and I'll come to this a bit later, is that ability to compare with crude oil cracking species. Okay, the idea is that you can co-feed. This is what Petrobras kind of led the way to doing, is co-feeding biomass feedstocks along with conventional crude oil feedstocks. Okay, to try and use the same catalyst or just modify it slightly. Much easier to modify a chemical process than it is to start again, really. So this is what these guys are kind of leading the way in at the moment. If any of you are interested, I'm sure the slides are going to be shared. So if any of this interests you, this is where you can find all of them. What I was trying to say with this slide was a number of collaborators I was exposed to during my time at the Catalysis Hub. I'll say the time counting is about 12 different institutions or organizations there that we got to work with, and particularly the ISIS neutron source, where all of this was made possible. Now, how long have I got, Chris? 15 minutes. 15 minutes, okay. So we're actually going a little bit earlier, that's fair enough. Okay, so I did want to talk about what's, I think, might be next in the field. Okay, so this is where discussions of people all throughout, both at ISIS and at different conferences and all this kind of thing. So increases in instrumental flux, that's sometimes what stops us from doing the stuff that you guys could do with kind of optical techniques, all right? So recently, the Tosca spectrometer at ISIS had its guide upgraded, and that increased flux by a factor of 50. That meant that rather than having to take 20 grams of zeolite powder, pack it into a cell at great stress, and put it into a beam, leave it for 2 days and see a tiny peak, I could put a couple of grams in and see really well resolved Bronsted acid sites inside that zeolite sample. It's completely changed the science that we're able to do. But here's what we get to move away from ex situ studies, and I know work like Ian and others who are working on these, building cells so that you can do things like flow through, have flow through kind of cells, so you can flow the gas through and watch things like the diffusivity change or watch your spectra change, which you never really got to do before. Possibility of spatial resolution. Now, these beams are often quite diffuse, so with the right sample cell, perhaps there's a chance you could have a bed and you're able to sample diffusivity at different parts of that bed. How interesting would that be? You could do that. That is a possibility too. Now, more realistic experimental studies. Now, the great thing, I didn't mention this earlier, is that the minute you deuterate part of a mixture, that just removes its signal from the neutron spectrum. So if you had a situation where you're trying to look at competitive diffusion or even competitive reaction with certain species, if you have one that's deuterated, that removes it. So then you deuterate the next one and you can see how one's behaving, right, in your spectrum. Okay, so very, very interesting work. And I believe there's a world-class deuteration facility at ISIS as well. I think we're going to start using a lot more of those. Now, defective and failed systems. This is one point we make a lot about comparing and modeling. We're always kind of looking at a kind of pristine system, and in catalysis, we'll often start by looking at relatively pristine systems. We're going to move away to these more messy systems. Everyone knows that after milliseconds of a catalytic reaction taking place, it stops being that nice, tidy system we all like to imagine it as, and it becomes a real mess. So we're going to start moving towards these kind of parametrically defective systems. I'll talk about coking, so being able to coke the system properly, but crucially, you need that proper characterization. It's all very well and good me saying this system's coked, so it's moving more slowly. Well, yeah, what kind of coke is it? How much of it is it? How long did it take to build up? Okay, this is the kind of thing you need to know if you're going to optimize a catalytic process, and these molecular behavior studies are actually going to make a difference. Finally, so we get to talk a little bit about classical simulation. So one thing I showed you is that we can reproduce Quench spectra. Typically, when you're parameterizing a classical simulation, that would come from density functional theory calculations, or that would come from absorption energies, things that aren't necessarily looking over the same scale, right? We can actually use things like Quench experiments to measure rate of rotation, measure lengths at acidic sites. We can use that to parameterize classical simulations too. That's something that we like to start doing. Again, as I've said, both with experiments and ex situ or in situ, whatever you want to call it, we need to make this essential move away from these model systems, okay? As I said, milliseconds into a catalytic process, it stops being tidy and becomes a mess. We need to find a way to model the mess properly, okay? This could include in zeolite catalysts, at least kind of using these kind of big silanol defects, silanol nests, the corresponding extra framework aluminium that lives in the framework. You need to know exactly what kind of eval it is, extra framework aluminium it is. That needs to go hand in hand with proper characterization of your samples. So all the modelers need to be working directly with those who characterize the systems, make sure you're modeling exactly what it is. Grain boundaries, again, this is moving on to kind of multi-scale problem. Okay, a lot of interesting stuff happens at the boundaries and surfaces of crystals. This needs to work in, and I really think the neutron optical spectroscopy techniques will make huge difference with this. Coke. So I've put Coke in inverted commas here because defining Coke is a non-trivial thing. Now, there's been some really interesting work by Stuart and others who have been able to show that it's kind of like glassy carbon. Some people consider that hydrocarbon pool itself and its deposits, they would call that Coke too. You need to know what type of Coke's in your system. How are you going to model Coke classically? Okay, that's actually quite a significant problem, but you need to know what the Coke is before. You could probably model glassy carbon classically. There are potential to do that, and there's ways to do that. What I want to say is that clear and detailed characterization is crucial at all these steps, okay? And while we're doing this, we need to really be modeling the two and studying as well differences in activity and selectivity, okay? Just to make sure we're sure that this molecular behavior is actually seeing what comes out of the catalyst afterwards. As with that, there's going to be quite a few acknowledgements. If you bear with me, as far as I'm concerned, this is all their medal too. All right. So I'd like to thank my supervisor, so of course Richard, where I began my PhD at Harwell, and continued support Stuart Parker and Nora Duluth for my postdoc time at Cardiff. Everyone I've worked with at ISIS, so this is Victoria Garcia Sakai, head of molecular spectroscopy now. Ian, who I've worked with a number of times. Franz and Jeff, who I work with on a lot of simulation work as well. Support scientists too, so that's Sarah Langham and Mark Kibble. I didn't break anything too bad, and if I did, I at least fixed it before you got back on Monday. And then in terms of my studies themselves, this is Carlos Hernandez Tamargo, who I work with on the biomass. Arun and Matt, who works with me on the methoxy study. Russell and David, I'd love to work with these guys again in terms of looking at some catalytic fouling in the system and how these molecules behave. Santosh, who I still work with plenty to this day. Johnson Matthew, so that was the work on the SCR. That was a really fun collaboration with Ian Hitchcock, Andrew York, Misbah did the modeling, and Paul Collier. Catalysis Hub, so Josie Goodall and June Callison, who are now watching, everyone at Catalysis Hub. These two, they support my student, well, they supported myself during my work and postdoc at the Hub, and support one of my students to this day, so I'm grateful to them. Nikos and Peter, for when they both started and the Catalysis Hub started, turned that place into a world-class place to study catalytic science very quickly. And all these people who made daily life quite a lot easier while I was there. Okay, I'm not sure who this mediocre-looking boy band is, but that's us. And everyone above too. Okay, so Matt Davidson is awarding me the Warwick Fellowship and a chance to assemble this team of absolute superstars. This is Alex Porter, Claire Woodward, Katie Morton, and Sandra McHugh. Look out for those names. They'll be leading soon enough. Steve Parker, a great mentor. Ace Sarbayeva, fantastic mentor in zeolite science, and Steve Parker in terms of modeling too, and we carry on with our work on diffusivity in zeolites, MTH, ligand cellulosic biomass, and some other work we branched out to in drug delivery too. There'll be a lot of neutron beam time, and every one of those will have a complementary calculation to go with it. And with that, I would like to thank funders, of course, Roger and Sue Warren for my current fellowship, the Ramsey Memorial Trust for the Ramsey Fellowship, where I did a lot of this work. And finally, I just want to thank the JMT panel for looking on this work favorably. It really means a lot. And I hope one thing we can show you is that we are just getting started. I think the next 10 years are going to be so exciting as the technology increases in its capability. And I look forward to updating you over the next 10 years or so at these kind of meetings. So thank you all so much for listening. Thanks a lot.
Alex, thank you very much for a wonderful award talk. The floor is open for questions.
I've got one question, you've been talking about all the gas phase reactions.
Yeah.
What if we now, can you do experiments with solvents, which obviously would be interactive, and looking at proton reagents? Is that possible? And look, I just have a feeling that you're probably not exploring as much of the zeolite pore structure as you've got solvents there as you do with the gas phase.
Yeah.
So, do you want to comment?
It's really quite tough. In terms of saturating your spectrum, that's an issue. You make the point about deuteration. In a bronze acidic zeolite, sorry, you've got HD exchange going on like there's no tomorrow. And that's why there's an issue with that too. I expect these increases in flux will make a difference. One thing that is really important is performing the correct subtraction with data. So in soft matter, they do this kind of thing all the time. In soft matter, they're always dealing with liquid systems and these very kind of mobile, very exchanging systems, the subtraction step. And I think there's probably going to be quite a lot we could learn from the soft matter community when it comes to dealing with these neutron techniques in catalysis in terms of subtraction methods that are going to come from that. I'm sorry, that's all I can give you so far. But I would suggest that the point you make is right, especially about when it comes to liquid phase catalysis. But I think there's a lot we can learn from soft matter about that. So we'll see.
My feeling is in the liquid phase, actually, we're only looking at the external
Sure.
changes or
Right.
force of the zero.
Okay.
The
Yeah.
gas phase is
Of course. Yeah, you're right. That's a very good point.
different.
No, thank you.
Look forward to seeing it.
See, hi.
First of all, many congratulations. This is a
Thank you.
really nice book. So I'm most interested in this flexibility or the dynamic process of the zeolite carbon absorption of the substrate. I just wonder what's the impact of this flexibility to the modeling of the diffusion of the substrate.
That's actually something that all the way from the beginning, which I found fascinating. So when you model the zeolite as a rigid framework, what you do is you create a lot of potential energy traps within the zeolite crystal, and molecules can fall into that and kind of stay there in a way that they wouldn't do if the zeolite is flexible. There was this absolutely fantastic, really interesting phenomenon called, what's it called? The levitation effect. Have you heard of that? So the levitation effect is whereby you have a molecule that's almost the same size as the pore. And if it's almost the same size, rather than rattling around if it's too small or just not being able to move if it's too big, the kind of the repulsive and the attractive forces almost cancel out, and you see a massive increase in diffusivity. It will just almost levitate down. And it was fantastic until we allowed the framework to breathe, and that didn't exist anymore. Okay, there's also something called resonant diffusion. That was where a molecule of a certain shape, a certain size, sorry, you'd see examples of where C12, so C12 dodecane, was moving faster through the crystal than C8, so octane, was moving through. That was because it was the exact right shape to fit in ZSM5 between the two intersections, and it would stay there. Allow that framework to breathe, that stops happening. So qualitatively and quantitatively, the implications are massive. Absolutely, absolutely massive. And I'm not going to suggest that, because there are some times where these effects have been seen experimentally. So I'm not suggesting that it's not possible. I'm not suggesting that they don't exist. I'm suggesting that the way we were modeling was perhaps exaggerating these effects in ways that weren't necessarily the case experimentally. So does that answer your question?
Yes.
Okay, thank you.
Keith.
So I guess my question is about speculating whether you talked excellently about breathing and the zeolite framework, whether you can try to improve or modify that, because obviously as an industrialist, like some new materials that might be commercialized, right? Can you look at things like the silica to alumina ratio and structures and how that affects those processes, and pragmatically look at materials that might be synthesized in the future and see how those impact those phenomena.
Sure, Andres, I believe you could look at it. Now, an issue with looking at things like silicon to aluminium ratio in terms of how the molecules behave is that when you add more aluminium, you add more absorption sites, right? So you can't necessarily be sure that it's the impact in absorption sites or the impact in flexibility. Now, there are some very, very absolutely fascinating pressure studies on the structure of zeolite. So modeling at sorry, not modeling, but performing experiments, which you can do very well with INS. So researchers such as Ace Saltbayeva, who I mentioned, they look at these kind of high pressure systems and how flexible the systems are. There's this idea of the flexibility window and how that changes things like silicon to aluminium ratio. So yes, in terms of modeling will play a huge role. It's going to be about, and then machine learning will play a role in here, but I don't like to use that word without knowing exactly what I'm talking about. Being able to model thousands upon thousands of systems at any one given point in time will give you a huge amount of insight into the basic fundamental physics of these systems? So the short answer is yes. It's complicated and it will involve a lot of work. I believe so.
Stuart?
Well done, Alex.
Cheers.
You said the next stage in computational modelling is to model the mess.
Yeah.
Clearly, probably the way forward on that is it just means it's going to be a much bigger model and just take advantage of increased computing power. An alternative might be to sort of empirically model it, because what's done for a lot of the diffraction type things, the reverse Monte Carlo things, the UPSR thing, is essentially you tweak your potentials to fit your data. Is there a possibility to be able to do the same trick with classical MD for diffusion processes?
Yeah, this comes a little bit to what I was talking about, how when we're reproducing these kind of spectra and we're fitting the potential to then reproduce that spectra. That's a big part of it. What we would then do is we do the same thing with those spectroscopists. So I think it's now starting. I know there's some, I can't remember the acronym for it, but I know something is being generated in scientific computing to create these kind of machine learning based kind of reverse Monte Carlo techniques too. In terms of modeling the mess, it's tough because you could start, again, if we look, so should we use Coke as an example? Every system is going to be slightly different, right? Depending on if you ran the reaction for 10 seconds longer, it's going to be a slightly different system. So you have to be careful of that. There's still always going to be approximations. But I think it's going to be much more based on this detailed kind of characterization, like when yourself and Andrea and others, we're looking at the types of coke that was building, whether it's glassy carbon, whether it's more just kind of ordered aromatic species and all this sort of thing. So it's about knowing what's next and then having effectively a potential library that could deal with that. And but now again, as you made about increases in computational power, it's just a case of having people ready to put the time in, or at least having codes, whether it's machine learning based or not, to create these potential libraries that one could select from.
Thank you. Josie, are there any questions from the chat?
There aren't.
All right.
Okay.
Yeah.
Well, I think we should leave it there and congratulate Alex for a great talk. And,